derivatives of trig functions. So what I've got here is, we'll start with sine. Would you agree that that's your normal sine graph? And on the graph, we've got a tangent drawn at 0. The slope of this tangent happens to be 1, so you see a dot there. Now if I drag this point along, okay, you notice that my slopes are getting flatter. Until I get right here at the top, my slope is going to be 0. If I keep going, now my slopes are negative. There, until here again it's equal to 0, and then it goes up again. So if we were to draw our derivative based on our original curve, what do you think the equation of the derivative of sine is going to be? It's going to be cos. And if we look at our cos graph, so here's our cos graph. Starting at 0, can you see that your tangent is completely flat at a maximum? And as I go this way, my slopes are all negative, and they're going to stay negative until we get to this point where it's flat, where it's going to be 0, and then now they're all positive. What's the equation of that blue graph? That's a negative sine graph. And not so easy to see. Those first two are pretty easy. But if I took a tan graph and I dragged, okay, so there's, I have sort of something kind of looks like a parabola there. Can you see, even if I keep going, that my slopes are always positive? I never have a slope on tangent. I never have a tangent on tangent that's negative. Now, what does that graph look like? Something kind of like one of those ones that has a bunch of u's, but cosecant and secant had a u on the top and a u on the bottom, right? And this one has only the u's on the top. So it might you might think maybe it's the absolute value that would do that, or another way to keep everything positive is to square. So the derivative of tan is actually secant squared. So just when you thought you didn't have enough things to know or memorize, now we have some new ones. But hopefully that picture, and hopefully you could keep that picture of in your head of me drawing the curves on there. I find it actually with sine and cos, I always think of these graphs, particularly with cos. What happens if I start here and as soon as I go to the right, can you see that my slopes are negative? And in order to have that below here, that'll help you remember that the derivative of cos is a negative sine graph, because immediately once we started with our slopes go into the negative right away. And if you think about your sine graph, well, right at 0, that slope is positive, meaning it's going to start at your maximum. So the derivative of sine is a positive cos. So that's how it helps me remember that the derivative of sine is positive cos and the derivative of cos is negative sine, because they can be easy to mix up because they go together and one is positive and one is negative. So now we can do all of our rules that we've had up till now with sine and cos as well, and tangent, we'll get to that soon. Now this one's going to have a chain rule. And this is a hard one to see the chain rule, because if you go to hug that function, and I know you like to hug functions, but you would tend to say that you'd hug the sine first. We have to remember that, and sometimes it's more helpful to remember that that 4 in there means this whole thing is to the power 4. We don't write it that way. We write that 4 in between the sine and the x. But this is what it actually means. Sine x times sine x times sine x times sine x. And if you take the time to write it out like this, can you see when you hug it, you'd get the exponent of 4, as your outside function. Whereas you might think when you look at the original function that your sine x is your outside function with the 4 inside of it, just how it looks. But in reality, this means all of sine x is to the power of 4. So our derivative, it's going to be a chain rule. You bring the 4 out in front. You always keep the inside the same. Subtract 1 from the exponent, multiplied by the derivative of the inside. The derivative of sine is cos. So when we go to hug this function, hugging it from the outside, you hit a coefficient of 4, yes? Well, hugging a function, because I always talk about your outside function and your inside function. Because when you have a chain rule, you do the derivative of your outside function first, and then your derivative of the inside function. So when I try to envision what does my outside function look like, I have to come from the outside, which is kind of like a hug. Okay? I don't know if that's, maybe this is a terrible analogy, but I like math, so I think about hugging calculus. Could be a good thing, not sure. But you have to decide what's your outside function, what's your inside function. Maybe it's easier for you to look at insides first. Like what is the most inside thing in this one would be the 3x cubed. And that 3x cubed is inside of a cos. Is the cos inside of something else? No. There's a coefficient of 4 in front, but your outside function for this one is going to be cos. So when we do the derivative of our outside function, and we say our outside function is cos, what's the derivative of cos? Negative sine. So our equation will start with a negative sine. We keep the inside function the same. Chain rule says then multiply by the derivative of the inside function, which is your 3x cubed. The derivative of 3x cubed is 9x squared. Of course, if you're writing this later, if you're simplifying this, you'd multiply your negative 4 and your 9 together. You would write your x squared out in front, because we want to make sure that we recognize that the only thing that's inside of sine is that 3x cubed. That 9x squared is multiplied afterwards, so you would probably write it in front like this. What kind of rules do we have for derivatives? Here we're going to have a product rule. Do we have any chain rules? Do we have any functions inside of other functions? No. So dy dx is going to be a product rule. Keep one of them the same. Derivative of the other one, derivative of cos, is a negative sine. Plus, keep the other one the same. Derivative of the first one, bring the 7 out in front, subtract 1 from the exponent. We get 21x to the 6th. Yes. Oh, yes. Thank you for noticing that. I didn't see the sin when I did the question. Love it. Yes, it does mean a lot of things. You ready? Okay. Just going to move this over this way a little bit. The sin y does mean something. It means we can't get y by itself easily in this question. So it is related to what we did yesterday. This is going to be an implicit differentiation. So how do we do the derivative of sine of y? Thank you for noticing that. I totally just didn't read that sin. The derivative of sine is cos. So it would be cos of y times by dy dx. Because that would be, the derivative of sine is cos, but anytime we're doing a derivative with a y in it, with our implicit differentiation from yesterday, we do the chain rule and multiply by dy dx. So then to find our actual final derivative, you guys are so observant. We would divide this whole thing by cos of y. And there we have our derivative. I think that's a good example. Sometimes we get used to doing something where we only have to look at the right side of an equation, that you can do exactly that. Just ignore, right? And you have to be careful in math because we do that often. Find dy dx. As soon as you got, well, this is what happened to me. As soon as I got to this, I'm like, oh, I know how to do these things. I just look for the equal sign, and then I look on the right side of the equal sign and figure out what I need to do. Because on the left side of the equal side is almost always just a y. And then that's what I did, and I totally missed the word sign there and went on to do the equation without even thinking about that. Okay. Example, if f of x, I'm reading everything now, equals that, we want to show that the derivative is equal to cos 2x. So looking at sine x cos x directly, what comes to your mind as far as finding the derivative? We'll call this one method 1. When you see sine x cos x, what do you think of? Product rule? Okay, so let's do product rule as our method 1. If I was doing the product rule, I keep one the same. Derivative of cos is negative sine, plus keep the other one the same. Derivative of sine is cos. If I multiply these together, I'm going to get cos squared x minus sine squared x. And that's one of our identities. Cos squared minus sine squared is cos 2x. Method number 1. I like method number 1. Method number 2. Do you remember this identity? That 2 sine x cos x equals sine 2x? If you remember that identity, can you tell me what sine x cos x is equal to? If 2 sine x cos x is equal to sine 2x, what would sine x cos x equal to? Close. I could take sine 2x and divide it by 2. Careful, you can't cancel out those 2's, because the one is inside the function and the other one is just a coefficient. So then method number 2, I change my original function to write it as sine 2x with a half in front, or divided by 2. Does that make sense that dividing by 2 is the same as multiplying by a half? Now if I want to find the derivative, can you see that there's a chain rule? That the 2x is inside of sine. So we have one function inside of another function. So I would do the derivative of my outside function first. What's the derivative of sine? Cos. Keep the inside function the same. Multiply by the derivative of the inside function, which is just 2. And the 1/2 and the 2 cancel out, and we get the same result, which I think is pretty cool. Okay, I'm going to get you to do the next 2, and I'll put up the answers in a bit. Maybe 1. How did you do? Outside function is the cos. Keep the inside the same, and multiply by the derivative of the inside function. Did you get a chance to do the next one? Or you have a question about this one? Yes?